Let f denote a function with domain D sub f and range R sub f. Mathematicians often refer to f as a mapping from D sub f to R sub f. Consider any point A in its domain. Then A maps into its image f of A. Points close to A may all map into points remote from f of A. Or some of them may map into points close to f of A, while others go into points remote from f of A. Then again, it may be that points close to A all have their images close to the image f of A. This latter situation is given a name: continuity. Loosely speaking, we say that f is continuous at A if all points close enough to A map into points as close as we please to f of A. But to be precise, we must clarify what we mean by the expressions close to and as close as we please. For this, we use the concept of neighborhood. In one-dimensional space, a neighborhood of a point is any open interval containing it. That is, an interval excluding the end points. Every point has an infinite system of neighborhoods of arbitrarily large and small sizes. In two space, a neighborhood is an open disk, the interior of a circle. In three space, an open ball, the interior of a sphere. For a given point A, preference is often given to the concentric system of neighborhoods centered at A. They occur in arbitrarily large and small sizes. A neighborhood is easily described in terms of distance. For a given point A and a positive real number R, the so-called R neighborhood of A, denoted by n sub R of A, is the set of all points P at a distance less than R from A. Every neighborhood of a point A contains an R neighborhood of A. In fact, an infinite system of concentric R neighborhoods of arbitrarily small size. We can now define what we mean by continuity precisely. F is continuous at a point A in its domain if and only if, for every neighborhood U of f of A, there exists a neighborhood V of A, such that every point of the domain inside V has its image inside U. We can state this in terms of distance. For every positive number epsilon, there exists a positive number delta, such that for every point x in the domain of F, if x is within delta of A, then the image f of x is within epsilon of f of A. Or equivalently, in terms of sets, the part of the delta neighborhood of A in the domain maps into the epsilon neighborhood of f of A. We can understand continuity better if we contrast it with the opposite notion of discontinuity. F is discontinuous at a point A in its domain if and only if there exists some neighborhood U of f of A such that For every neighborhood V of A, there is some x in V and in the domain of F, for which the image f of x falls outside of U. The definition of continuity applies to a wide variety of mappings. For example, the domain and range may both be on the real number line, or the domain may be on the real line and the range in the plane, or vice versa. Or the domain may be in 3 space and the range on the real line, or vice versa. Or the plane may be both domain and range, and so on. Consider now 2 mappings, a mapping G and a mapping F. Suppose the range of G and the domain of F have points in common. Then we can form the composite mapping G followed by F, denoted by F circle G. The domain of F circle G is the part of the domain of G which maps into the domain of F. For every x in this domain, F circle G of x is F of G of x. Let A be a point in the domain of F circle G. Suppose F is continuous at G of A, and suppose G is continuous at A. Is the composite F circle G continuous at A? The answer is yes, and the proof is easy. Take any neighborhood U about F circle G of A. Then U is a neighborhood of F of G of A. And so by the continuity of F at G of A, there is a neighborhood of G of A. Call it W, all of whose points in the domain of F map into U. On the other hand, the continuity of G at A demands that corresponding to the neighborhood W, there exists a neighborhood of A, call it V, all of whose points in the domain of G map into W. But points taken by G into W are thereupon taken by F into U. So points of V, which are in the domain of the composite F circle G, are mapped by F circle G into U. Since in this way a neighborhood V can be found for each U, the proof is complete.